If you're taking the Cambridge IGCSE Physics 0625 paper, here is a pretty brutal truth you need to hear right now. Top-tier students, the ones who literally have every formula memorized by heart, are actively hemorrhaging marks on Phys practicals. I'm talking about throwing away entire grades on questions you actually know the answers to, all because of how you're writing those answers down on the page. It's not a lack of knowledge that's capping your grade, it's a lack of translation. You know the physics, but you're failing to communicate it in the precise language the mark scheme absolutely demands.
So here is the confession. Even the absolute most prepared students failed to secure top bands because they completely ignore the examiner's specific command word expectations. Look, Cambridge examiners are not mind readers. They are actively hunting for very specific triggers. You might fully understand exactly how a spring stretches under tension or the mechanics of how a ruler balances on a pivot, but if you don't package that knowledge exactly how the mark scheme expects, they just aren't going to give you the marks. It's a harsh reality for sure, but once you understand it, you can completely manipulate it to your advantage.
Think about the painful traps you might be falling into right at this very moment. Missing your units on a final answer, rounding your intermediate values way too early in a multi-step calculation, giving these super vague explanations like, it gets bigger, or making critical graph axis errors. And by the way, making a graph axis error doesn't just lose you 1 mark, it cascades. It ruins your final calculation and wipes out your entire answer for that section. These mistakes instantly cap your grade boundaries, and if you don't correct them right now, you are literally just leaving easy, guaranteed marks on the table for someone else to claim.
This is exactly why your standard revision fails. Memorizing the textbook? Yeah, that just isn't enough anymore. Reading about forces and turning pages until you're blue in the face won't save you if you can't translate that foundational knowledge into examiner-safe language. Highlighting your notes doesn't build exam technique. We need to completely change your exam strategy today. We need a structural fix that automatically forces your brain to generate the exact phrasing the examiner has printed on their grading sheet.
The solution to this is what I call the 4-part mark magnet framework. This is a real game changer that will transform your answers from vague guesses to top band perfection. Every single time you face a difficult data analysis or practical question, I want you to run your answer through this specific filter. Step 1. State the fundamental physics concept. Step 2. Pull evidence or data directly from the question or graph. Step 3. Apply deep scientific reasoning. This is where you explain the why behind the data, connecting the numbers back to the physical laws. And Step 4. Wrap it all in precise examiner wording. When you combine these 4 elements, your answer becomes completely undeniable.
Let's actually apply this framework to our first quick win. Step 1 is the concept. For Hooke's law, you absolutely must ground your answer in exact, exam-safe physics terminology. Saying something like, the spring stretches when you pull it, gets you nothing. It has to be, the extension of a spring is directly proportional to the force applied, provided the limit of proportionality is not exceeded. Memorize that exact wording. The phrase, provided the limit of proportionality is not exceeded, is the magic key that unlocks the final mark. That right there is your mark magnet.
Next, let's think about the experimental variables for stretching that spring. Getting your table design and units wrong here is a fatal error in any practical paper. Your independent variable is the force, measured in newtons. Your dependent variable, which is the one you're actually measuring as a result, is the extension, in millimeters or centimeters, and your control variable, that's the specific spring used. If you change the spring halfway through, you corrupt your stiffness constant and your data becomes entirely invalid. If a question asks you to design a table, these headers and units must be explicitly stated if you want full marks.
Now I really need you to stay with me here, because in a moment I'll show you the hidden graph axis clue that changes the answer completely. But first, you need the framework that makes that clue obvious. If you miss this specific visual cue on your exam paper, your data analysis falls apart entirely, and literally all your subsequent calculations will be based on a flawed premise.
Because if you don't use the framework and you miss that clue, here is exactly what score you're going to get if you try to calculate your spring constant but round your values too early during your working out. 0 marks. Cambridge examiners are totally ruthless when it comes to premature rounding because it creates compound errors in your final gradient or constant calculation. Think about it. If you round 0.333 to 0.3 in Step 1, your final answer in Step 3 is going to be wildly outside the acceptable tolerance range. Never ever round until the final answer.
Okay, it's time to put you to the test. I want you to pause and predict. Can you spot the examiner error in this typical student's conclusion to a data analysis question? Imagine a student looking at the raw data for a stretching spring experiment and writing down their final answer to summarize the relationship.
Keep our four-part framework in mind: concept, evidence, scientific reasoning, examiner wording. Let's see what they actually put down on their paper. So the flawed student answer reads, "The spring stretched more when heavier." Why on earth does this score a 0? Well, it lacks quantitative data, it lacks scientific reasoning, and honestly, the wording is just terrible. Now contrast that with a top band answer using our framework. Extension is directly proportional to force, supported by a constant gradient of 0.5 millimeters per Newton. Listen to how powerful that is. We've got the concept, we pull the exact 0.5 value as evidence, we apply the scientific reasoning that a constant gradient proves direct proportionality, and we use perfect examiner wording. It's totally bulletproof.
Right. The stakes rise now. We're moving away from stretching springs to moments and balancing a ruler to find the center of gravity. The practical design questions here are where top students really start to lose their grip. Moments are inherently trickier because you're dealing with a 2D problem where perpendicular distances matter just as much as the applied forces. And frankly, the margin for experimental error is huge.
When students are asked to design a practical investigation for the center of gravity, they fall into a rapid-fire trap of errors. They select the wrong distances to measure, often measuring from the end of the ruler instead of the actual pivot. They offer incredibly weak practical improvements when asked how to make the experiment more accurate. They write conclusions that straight up contradict their own data table. And worst of all, they completely ignore anomalies, pulling flawed data points into their moment calculations without a second thought. Before we fix those errors with our framework, let's make sure we lock in the core concept. The center of gravity is the point through which the entire weight of an object appears to act. This definition is your absolute anchor for scientific reasoning. If an exam question asks you to explain why a ruler topples, your reasoning must trace back to this exact concept. When the center of gravity shifts past the pivot point, it creates a resultant, unbalanced moment, causing the object to rotate. That is the exact depth of scientific reasoning examiners want to see.
And this perfectly illustrates how we apply Step 4, examiner wording, to a practical scenario. A really common question asks for a practical improvement for a balancing experiment. The flawed check is simply writing, "Make sure the ruler is flat." Like we said before, that gets you nothing. The examiner's safe check is, "Ensure the ruler is perfectly horizontal to the bench to avoid parallax error and improve accuracy." By naming the specific error, parallax, and giving a precise action, you're showing the examiner you truly understand the physical limitations of taking a reading by eye. That's guaranteed marks.
All right, it's time to reveal that hidden graph axis clue I promised you earlier. Before you ever calculate a gradient for a spring constant or a moment, you must physically check the scale for anomalies and confirm reliability. Examiners deliberately plot one point slightly off the trend line just to test your awareness. If you blindly pull data points to calculate your gradient without drawing a true line of best fit that actively ignores that anomaly, your final calculation is totally doomed. Always hunt for the anomaly first, circle it, and exclude it from your math. But here's the harsh reality of it all. While you now know the specific practical traps for Hooke's law and center of gravity, and you have the four-part Mark-Magnet framework firmly in your mind, applying this to complex evaluation questions is an entirely different beast. Knowing the traps for practical setups is one thing. Evaluating competing datasets under intense exam time pressure is an entirely different level of difficulty altogether. Honestly, this is the final boss to the 0625 paper. So the ultimate question remains, how do you apply this Mark-Magnet framework to the absolutely hardest evaluate questions on the entire 0625 paper? You know the ones, where they give you two students conflicting experimental results and ask you to judge who's correct? You need a highly specific vocabulary for this. If you don't know the exact evaluative wording the mark scheme requires to compare data reliability, you are going to stall out at a B grade, no matter how good your math actually is.
To secure those absolute top grade boundaries, mastering the evaluation framework isn't optional, it's mandatory. The correction sequence continues directly in our next explainer, where we're going to crack the code on the Physics 0625 top band evaluation framework. We'll look at exactly how to weigh competing evidence and write evaluations that literally force the examiner to give you every single mark. You cannot afford to skip this next step in your exam strategy.
The tools are right in front of you, but you need the final piece of the puzzle. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click the explainer on your screen right now to master the evaluation framework. But before you do, just ask yourself, if you walked into your physics paper tomorrow, would your answers truly pass the Mark-Magnet test, or are you still just relying on hope?